Good afternoon, everyone, or good morning, depending on your time zone. Welcome to the invited talk by Dr. Skevi Perdikou with topic Landslide susceptibility mapping using satellite radar interferometry. We will start with a short welcome note by Dr. Kyriakos Themistokleous, and we will then proceed to the talk. The talk will be recorded, so please turn off your cameras and microphones. We will allow questions only through the chat, and they will be answered after the talk. At this point, I would like to invite the project manager of the EXCELSIOR project, Dr. Kyriakos Themistokleous, for a short welcome note.
Okay, Lenny, do you hear me?
Yes.
Okay, thank you very much. First, I would like to thank Skevi for presenting today for this event. And also, I would like to thank everybody for participating today to see what Skevi is doing and what she's going to present to us. I know Skevi for the last 10 years, and she's been a valuable contribution to research. And not only that, we have done a lot of projects together. And we cooperated with her company for various events and projects. Thank you, Skevi, for supporting us, and thank you for being here today to show us what you're doing, and not only that, but presenting us all this research about the landslide mapping using satellite radar interferometry. Okay, if you hear me, Skevi, go ahead. Will be.
Thank you, Kyriakos. We will now proceed with the talk. So, Dr. Skevi Perdikou is an experienced satellite remote sensing and geotechnical expert at the consultancy Geofem Ltd. She holds a Bachelor of Engineering in Civil Engineering, a Master of Science in Geotechnical Engineering, and a PhD degree from the University of Southampton in Satellite Remote Sensing. Her combination of engineering and satellite remote sensing skills enabled Geofem to offer advanced Earth observation techniques for engineering applications and interpretation of results. She has worked on many research and commercial projects in satellite remote sensing using both optical and radar data. Some of her projects include the use of satellite radar data for ground and infrastructure movement monitoring for landslides, transportation networks, forensic investigations, urban monitoring in Cyprus and around the world. She has also performed many research projects in the field of satellite remote sensing funded by national sources, the European Union, the European Space Agency, and the private sector. So, Skevi, now the stage is yours. I think you can also share your screen now.
Hello, everyone. Can you hear me?
Yes.
Can you see my screen?
Yes. If you could please put it on full screen.
Yes, I will. And let me just show my camera. Just a second. I'm trying to. Okay. All right. I think we are ready. Okay. So I think now you can see the first slide, correct? And
yes,
the camera.
great.
Okay. Great. So first of all, thank you very much for organizing this great event and this series of great talks. and thanks for inviting me today to talk about our work here at Geofem. So first of all, I'd like to say that during the presentation, you can have your questions on chat, and I have a colleague of mine, Dimitris, who will be able to assist me in answering these questions during the presentation, or we can answer the questions and have a discussion at the end of the presentation. So the talk today is on landslide susceptibility mapping using satellite radar interferometry. And the outline of today's presentation, I would like to start with describing the main principles of differential interferometric synthetic aperture radar, then present landslide susceptibility mapping work we are doing here at Geofem, and we can have a discussion and answering any questions at the end. Few words first about our company. We are a geotechnical engineering consultancy with expertise in Earth observation. And by combining this engineering and satellite remote sensing expertise, it allows us to provide informed, cost-effective infrastructure asset monitoring without the need to visit the sites, and to offer applications of satellite technology in geotechnical engineering. In our company, we have expertise in geotechnical engineering, satellite image analysis, in GIS, and in programming development. So let's start with the principles of differential interferometric synthetic aperture radar. Let's see first what satellite radars are. The satellite radars are active systems, which means they send out electromagnetic radiation on the ground and they record what's reflected back from the target, from the ground surface. This is different to the optical sensors, which rely on sunlight. The optical sensors measure what's reflected from their surface from the sun electromagnetic radiation. The fact that the active systems send out their own radio waves and record what's reflected back means that they not rely on sunlight, so it means they can work day and night. Also, because they operate in microwaves, which can penetrate the clouds, they can operate under any weather conditions, which is a great advantage. And also, another important thing we have to have in mind is that there is freely available data since 1992 from the ERS 1 and 2, ENVISAT, Sentinel-1. And since November 2014, with the launch of European Space Agency Sentinel-1 A and B, we have freely available data with coverage of the whole of Europe with every 6 days data availability, but also with coverage almost anywhere else in the world. So there is coverage in the US, in Africa, in Australia, not in both orbits, but for some areas, both orbits as well. So let's look at the electromagnetic spectrum. So if this is the visible spectrum here with 0.4 to 0.7 micrometers, and the optical sensors cover the visible infrared and the thermal bands, the radar satellites, they cover electromagnetic spectrum into centimeters. And these are the different bands. So the presentation I'm going to show you today refers to the C band shown here with the Sentinel-1 data. So let's look at what we measure from satellite radar systems. We have two main parameters. One of them is the amplitude of the radar wave, which is the height of the wave shown here as measured from the highest point. And the amplitude is related to properties of the ground surface. One such example is the soil moisture, and we have performed a lot of work in this area where we associate the signal from the satellite radar images with the soil moisture changes on the ground. The other very important parameter is the phase of the radar wave, and actually the phase difference is used for measuring the displacement. So we can see the location of a point within a wave cycle here. So let me explain the phase difference in this figure, which is shown very clearly. So a satellite radar passes over a point over an area on the Earth's surface, sends out electromagnetic radiation, which hits the ground surface. Let's say our ground surface, the initial ground surface is shown here in a dotted line. So it hits the ground and then is reflected back, shown here in solid line. This is pass one. So our radar satellite records the reflected radiation. A few days later, the same satellite passes over the same area on the Earth's surface, sends out electromagnetic radiation, which hits the ground, but in the meantime, our ground has subsided from here to this new location. So the electromagnetic radiation hits the ground here, and it is reflected back, shown here as a dotted pass two line. What there is here, we notice there is a phase difference between the first pass and the second pass. So this phase difference can be converted with mathematical equations considering the wavelength of our satellite, and can be converted into displacement. And actually this coloring scheme you can see here, it can help us in two ways. It can help us to identify whether we have subsidence or uplift. These are called fringes. In interferometry, you will hear these words a lot. And also it can help us to determine the magnitude. So let's look at the sequence here. We have blue, and we have pink, purple, yellow sequence. So let's look at our example here. We have the blue, we have the purple, we have the yellow, we have the blue. It's exactly the sequence: blue, purple, yellow, blue, which means we're moving away from the satellite, which means we have subsidence because the ground has gone down. Also, you can see here the sequence of the coloring, which means it helps us determining the magnitude of the displacement. And this is the simplest form of the principle, and it works very well for when we have big displacement events like an earthquake, where we can take data before the event and after the event, and it allows us to measure the displacement. This is in sedimentary, in centimeters, sedimentary accuracy, but it's the principle based on which the methods I will describe in a bit help us identify slow movements as well as earthquake movements. So we do have ascending orbits, which we call ascending orbit when our satellite is moving from the South Pole, moving towards the North Pole, and records data to the east, shown here in blue. And when a satellite is moving from the North Pole towards the South Pole, and records data to the west. So every few days we have an ascending pass, observing the same position on the Earth's surface with data to the east, and few days later, 2-3 days, let's say later, we have the same satellite. We have another satellite observing the position on the Earth's surface from the descending orbit. The availability of ascending and descending orbit allows us to decompose the data, and in that way we can get the vertical displacement, shown here, and the horizontal displacement. Of course, the horizontal displacement, it's only available on the east-west direction due to the geometry of the satellites. Also, we can reproject the outputs into a customized direction. For example, if we know the slope of a hill or a mountain. So let's look at some popular techniques, and these are also methods that we have used in the examples I will show you for the landslide. So based on the principle I described earlier with the phase difference, we can use different techniques to achieve millimetric accuracy. The first one is the persistent scatter interferometry, PS technique is known as, and this technique generates interferograms, paired images between a master image and the slaves. What is a master? What are the slaves? For this technique, we need a bigger data set. So we cannot use 2 images, as I explained before, for an earthquake. We need a big data set. And from this big data set of 20+ images, one of them becomes the master image, and pairs are created between the master and each of the rest of the images, which are called slaves. With this method, we can perform analysis with millimetric accuracy, and this method is ideal for urban areas. The accuracy depends on many factors, amongst which is also the data set. Usually, if you have a greater data set, you improve your accuracy, but also depends on other factors that I will explain in a bit. It's also effective for cases where you have linear movements. And when I say linear movements, I mean increasing movement over time. The second technique, which is popular and also we have applied in our analysis, is the SPAS technique, which is based on, again, the big data set. But the difference with the previous one is that this one generates pairs, image pairs, between all possible combinations, provided they satisfy a threshold requirement. So the analyst can set up a threshold, because if you have, let's say, a data set running over a 2-year period, you can specify in the image whether you want each image to create a pair with the image with a subsequent date, with 12 days apart, 24 days apart, 60 days apart, 45 days apart. You can specify the time period where you allow your analysis to have a pair with. This method works also for rural areas, not only for urban areas, where you have semi-vegetated areas. The reason is because you have so many pairs in your data set, because you create all the possible combinations, and that allows you to remove the pairs with noise that they cause decoherence. Such examples could be when you have vegetation growth, and that we're talking always about sparse vegetation, not dense vegetation. So in some cases, you can remove the pairs that they affect most severely your coherence, and still manage to get good results. That's why I put here rural areas, semi-vegetated. We're not talking about dense vegetation or forested areas. And also, this method works well for nonlinear movements. And when I refer to nonlinear movements, I mean seasonal changes of movement, where we have the example of swelling clays. So what do we measure by this method, by DINSA? We measure the mean annual velocity of movement in millimeters per year. We can determine the displacement for each specific date in our data set. Also the total displacement within the study period, and the displacement is measured either along the line of sight of the satellite, in the vertical, in the horizontal direction on the east-west, of course, and also reprojected on a customized direction. Before we move to the landslide study, I will show briefly some examples of applications. This is for monitoring bridges. Each of these lines shown here, starting from this one here, this is our first data. It shows zero movement, zero displacement. This is the displacement with distance. Each of these lines show the progress of movement over time. So we divided the analysis over 3-month periods. Black lines are the ones for December 15 to February 16, and the second period, third period, and fourth period. And this distance here is this red line shown here above the bridge. So we have this bridge here and a second bridge here. So we wanted to investigate the reasons for problems appearing on this bridge under the red line, and what has caused these problems. This was a forensic investigation. And what we can see here, if we look at, let's say, purple line here, which shows data set September to December 2016. So let's choose one, which is one specific date. The displacement on 0.9 is 15 millimeters. So this is an uplift of 15 millimeters here, 0.9. And if we follow the purple line, we can see that at 0.10, we have a subsidence of nearly 20 millimeters. So here we have 15 millimeters uplift. Here, for the same date, we have almost minus 20 millimeter subsidence. So there is a differential settlement between 9 and 10 of nearly 35 millimeters for the same date. And also the area here is it's important because it's characterized by swelling clays over here. So this shows a different behavior on the effect on the bridge. So this is a method that offers us retrospective analysis and be able to analyze different projects. So this is another example where we can see a time series retrospective estimation of displacement. This is along a railway line. So we can see the problems here on this specific location with the data showing up to 30 millimeter displacement. This is a comparison between inclinometric and persistent scatter interferometry measurements showing good agreement. So we have validated our results for a different area. Another area is our application is the road network. So what we can see here, the green is stability, no movement. This is the velocity, and we can see increased velocities in this region here. Again, another example from the road network. This is an example in the United Arab Emirates, a road between Dubai and Fujairah. We can see here the mean annual velocity, and the displacement reaches 25 millimeters over the study period. For geotechnical structures, we have a reinforced soil wall here showing stability over the 4-year study period, while 500 meters to the east of this road section, we have an embankment, and we can see that at this location we have displacement in excess of 20 millimeters. Again, this is another example is the urban environment. We can monitor the housing and buildings in different regions. Mining, in the mining industry, we can see the boundaries of the longwall mining here. This is in a project in Australia. With red, we have the subsidence, so reaching 105 millimeters, and next to an urban area, which has uplift plus 40 millimeters per year, the velocities. So there has been monitoring, in situ monitoring from surveying along this road shown here in yellow. And what we have done, we have compared the surveying data performed by different contractors, shown here, with our satellite image analysis data, shown here, along the same road, and correlation coefficient was very high, 0.21. Very high also considering that the tolerance of the surveying method and equipment was plus minus 15 millimeters. The mining, again, that's another example with a railway line over a mining area. And we can see even identify the progress of works and the areas affected as the mining works are progressing. And this is an example I showed earlier with the road network that we had increased velocities in this area. This is an area in Paphos actually. And in the summer of this summer, actually in July, a sinkhole appeared on this exact location. So let's move now to the study we performed for landslide susceptibility mapping. So landslides are one of geohazards causing disruption in almost any part of the world. And between 1998 and 2017, the landslides affected an estimated 4.8 million people and caused more than 18,000 deaths. So this shows the severity of this geohazard. And due to climate change and the increasing world population with the movement of people in hazardous areas, it means that we are expected for these landslide events to increase in the future. And it is believed that 90% of losses due to landslides can be avoided if the problem is recognized prior to each event. This means that it is very important to have landslide susceptibility mapping. So it's very important to know which areas are at higher risk. Risk is something different, of course, but are at higher susceptibility of landslide. So let's look at the conventional and landslide inventories. These include extensive field campaigns, and they require experienced geologists, geomorphologists, and other specializations. They require analysis, gathering of optical satellite data, aerial photography, a lot of desk study. And these processes, these activities are time consuming, they require extensive field work, and they require very experienced personnel. This means that they are necessary, but they are impractical for regularly updated. It's not a process or an activity that can be, let's say, updated very, very regularly, especially when you have to cover large areas. If we consider that it is important to update landslide inventories with the addition of new and reactivated landslides, together with the availability of free radar imagery like the European Space Agency Sentinel-1 data, the development of different techniques of the INSAR, the availability of retrospective analysis for past and current landslide events, the large area coverage with single analysis offered by the INSAR, it makes this method an effective method for active landslide detection and efficient to provide regular updates. So this is a study area we have selected. This is Cyprus, so you can see it's to the southwest of Cyprus, covering some of the Limassol district and some of the Paphos district areas, with some areas of known landslide problems in, let's say, Armu areas, around Stados and a lot of other places. So these are some of these examples. Landslide near the village of Agios Dimitrianos, another failure of the road in Armu, shown here. So these are some of the examples that the people near these areas know very well. So the study area has steep, moderately steep topography. The geology comprises bentonitic clays and other geology, of course, but bentonitic clays are associated with swelling clay behavior. Also, it is important to mention here that in 2010, in the Paphos district, the Geological Survey Department, in collaboration with Scott Wilson Limited, they performed a study for landslide inventory, and they documented 1,842 landslides extending over 130 square kilometers in a total study area of 546 square kilometers. Some of the area that was covered from this study overlaps with our study. So let's look at the method we have followed. We perform persistent scatter interferometry in order to identify stable points. These are points that exhibit no displacement, as shown here. And these areas were selected as reference points for the flattening refinement process step of ESPAS. So it was used as input for the next analysis we ran. The next analysis was ESPAS, a small baseline subset analysis. The data set we have used were from 2016 to 2018. And we have used 47 images in an ascending pass, 48 images of a descending pass. I explained earlier what each of these passes are. The number of pairs that were created, the time between them, the temporal baseline was 12 days for each image. The threshold set for the maximum temporal baseline was 60 days. This means to create, it was, we allowed the analysis to create pairs between images that had up to 60 days difference between them. And the minimum and maximum normal baselines. So the use of successive images with high temporal resolution. So we used all the images every 12 days, allowed us to limit noises and artifacts due to atmospheric effects, but also due to growth of vegetation. And pairs that exhibit noise were excluded from the analysis. We have then proceeded with the decomposition of our results into true vertical and true horizontal displacements, into east and west direction, of course. And we have then proceeded with identification of landslides. We set up the threshold for that, and exhibiting velocities in excess of 30 millimeters per year were selected to identify the landslide. The reason for using this threshold, 30 millimeter and not smaller values, 20 or let's say 10 millimeters per year, it was to exclude soil creep, misclassified movements, and also due to results we had from some preliminary analysis we ran with from 2014 to 2016, and from site visits we were able to judge that this was the correct threshold to use. Here we have some of the results showing for the same area of interest, our study area, the horizontal velocity. So you can see here that our velocity with blue color, it's showing positive are movements to the east. So with blue is plus 79 millimeters per year. And shown here in Pissouri, it's movements to the east. And with the red color, we have velocities up to minus 86 millimeters per year. And this means because we had a 2-year period, study period, 2016-2018, the total eastward horizontal was 158 millimeters in the Pissouri area, and the total westward displacement was calculated at 172 millimeters in Ganna, shown here in red. Let's look at now the vertical velocity. We have the mean annual velocity in millimeters per year. It's 10 plus 10 millimeters, that means uplift, shown in blue. And the minus 60 millimeters per year subsidence, shown here in red. So the total subsidence observed within the study area for the 2-year study period was calculated at 120 millimeters. So let's see how we proceeded after our analysis. Each raster cell, let's say pixel, that exhibited velocity in either vertical or horizontal direction over the set threshold of 30 millimeters per year was characterized as an active landslide. With this, a total of 8,859 raster cells or pixels were classified as active landslides. So let's look at these raster cells or pixels we just mentioned. The blue and red here have to do with the training and validation datasets that I will refer to them later. So all of these points, both blue and red, they are the detected landslide raster cells pixels, which were classified as active landslides. And what we have done here, we have also mapped, we have also included in this the mapped landslides from the Geological Survey Department landslides. So what we can see here and what we have measured is that 61% of our raster cell pixels that were classified as landslides, active landslides, fall within the mapped landslides, shown here in white. The reason for only having 61% and not a greater amount, I think it's due to the fact that with our method, we only include the active landslides. The dormant or inactivated landslides were not included, because these could be landslides that do not show any movement, while in the landslide inventory by the GSD in collaboration with Scott Wilson, dormant landslides were also included. And also there is a time difference between the two studies. The landslide inventory was took place in 2010, by the GSD and Scott Wilson Limited, but our analysis considered data between 2016 and 2018. The next step was to study the effect of landslide contributory factors. We have the topographical ones. So we examined the effect that different and the collaboration between our displacements, movement as resulted from DINSAR with various factors. So the topographical ones we selected to examine were the slope angle. And the reason is because an increased slope angle is associated with increased shear stress in the soil, and with small angle slopes having low shear stresses, and there has been low frequency of occurrence. I have to say here that the literature suggests that very steep slopes do not show high correlation with the displacement. Sorry, not with the displacement, with the occurrence of landslides. The other parameter we examined in our study was the slope aspect. And this is related to the orientation of the slope, which is related to the sun exposure. And therefore, with how much sunlight, for how much period is exposed to sunlight, and the wetness conditions, and hydrological processes by evapotranspiration, which affect weathering processes. Also, the profile curvature was assessed, convex versus concave shapes, and there has been some association with erosion and hydrological conditions, and we show here what's considered. Positive is the concave shape, 0 is a linear, and the negative one shown here, this is a convex shape. So the shape of the curve was also considered. These are some of the results as extracted using a digital elevation model. So we have here shown to the left the slope angle. So 0 to 5 degrees, you can see here, this is the urban areas in Paphos. We have the flat areas, we have 5 to 20 degrees slope shown in yellow, and the different values of the slope. To the right, we have the aspect, the orientation of the slope, in other words. So green shows the east facing slope, purple are the north facing slope, blue the south, and yellow the west. Hydrological factors were also considered in this analysis. We considered the rainfall. The literature suggests that it is important to include also the intensity of rainfall for the occurrence of a landslide, but we have not included that because we have not had any data to be able to relate it to the occurrence of landslide. To do that, it would be good to have rain gauge data near landslides to be able to monitor the intensity of rainfall and associate it with possible association with the landslide occurrence. Because this data was not available, we used annual rainfall data, and this was in order to evaluate the distribution of rainfall, which remains relatively unchanged, and its association with the distribution of landslides. So the thinking behind this is that areas that receive higher rainfall, it's relatively constant over the years. So we wanted to see whether there is an association in the occurrence of a landslide in certain areas with the areas characterized by higher or lower levels of annual precipitation. Also consider the water flow direction, which is more useful if combined with soil property information for water infiltration rates, which we didn't do. We didn't consider the infiltration. The geology, which is found to be significant by many researchers in the literature, and also vegetation. The vegetation has been included by various studies in a form of land cover, land use, vegetation coverage, or classification, different types of vegetation. In our study, we used the Enhanced Vegetation Index in order to associate the vegetation coverage with the possible correlation with the occurrence of landslides. So this is the Enhanced Vegetation Index, showing areas of high vegetation here and low in these areas here. And this is the geological map as obtained from the Geological Survey Department. And we can see here the Monica, Naviu, and Berapedi formation shown in red, which is from literature associated with the landslide occurrence. So let's look at the next steps. So the landslide on the ground may be comprised of many raster cells or pixels. So we have to have in mind that a landslide on the ground comprises of many raster cells or pixels in our analysis, because each pixel exhibiting this velocity higher than 30 millimeters per year is considered as an active landslide. And for each of these pixels, the corresponding value for each contributory factor we just explained was determined. So each pixel was assigned a different value for each contributory factor. The contributory factors were geospatially analyzed with regards to the occurrence and distribution of the identified landslides. And this pixel by pixel multi-layer analysis enabled us to have a close representation of the topography. Because, as I said, one landslide on the ground could have many raster cells. Each raster cell may have different values. For example, for the curvature, we can have a raster cell that has a convex and the neighboring having a concave shape. This allows us to represent as close as possible the real situation. Of course, this is restricted by the resolution of our digital elevation model, which is a 30 by 30 meter spatial resolution digital elevation model that we have used for our analysis. We have then proceeded with the weight of evidence analysis. This is an index-based statistical method, which is used for predictive models and classification, and it has been widely applied for landslide susceptibility studies. And it is used in order to analyze the importance of each parameter. So we have used this method in order to find the weight of each of the parameters I mentioned, the topographical, hydrological, geology, and vegetation parameters. And these are the equations here. What we have used 70% of the randomly selected raster cells and pixels were classified as landslides were used for training, and the remaining 30% were used for validation. Now, for each contributory factor, the areas covered by landslide as well as the areas not covered by landslide were taken into account to derive the weight. So we have included both the those covered by landslide, but also the areas not covered by landslide in deriving the contrast weight, positive minus negative weight. In general, from literature, there are some ranges of weights which characterize the effect of the weight. So between 0 and 0.5, it shows that they could be characterized as mildly predictive, these weight values. Between 0.5 and 1, are characterized in some literature as moderately predictive, from 1 to 2 strongly predictive, and greater than 2 extremely predictive. Let's look at some of our results here. This shows the geology. The Moniengana view formation has a contrast value of 2.75, which is a very high positive number. So we can see a high association of this geological formation with the occurrence of landslide. The profile curvature, the concave, showed positive contrast value of 0.4, while the other showed negative, means no association. And with the rainfall, we can see here that the high rainfall showed a 0.99 contrast value. And this is, someone might think here, okay, the very high rainfall has shown lower contrast value, still high, but lower than the high. And someone might wonder why this is the case. This could be attributed to the fact that the very high rainfall usually occurs in mountainous areas, so in much higher steep slopes, like mountainous areas, and the very steep slopes are not usually have high correlation with landslide, maybe due to the geology. So because these parameters were studied individually and not as combination of parameters, it might be different geology in areas receiving very high rainfall. Still, both of them highly related. So this is our landslide susceptibility mapping. We show here the contrast weights, C, which are the ones we discussed now, were summed to derive the landslide susceptibility index map. We have 4 classes here. We have the no susceptibility, which is shown in dark green. These are the urban areas shown here in Paphos. Low, the light green. Moderate susceptibility with orange, and high susceptibility areas in high red. In high susceptibility in red. We have also proceeded with assessment of the model performance and validation of our results. The model's performance was assessed using the receiver operating characteristics curve analysis. The ROC curve indicated that the training of the model was successful, and the success rate was determined at 79.6%. And the testing of the model achieved a good result with prediction rate of 78.9%. And also we have validated our results against the mapped landslides shown earlier, and from the GSD, Geological Survey Department, and this indicate an 84% agreement for the moderate and high susceptibility zones. And this is a closer view of some of our results with the coloring scheme here. And shown here with black boundaries are the mapped landslides from the Geological Survey Department. And what we can see here is that we have quite a good agreement for some areas. Some other areas that are not mapped as landslides are characterized with high susceptibility in our case. This means that shows here, but usually they are in areas that they include some landslides, but we have shown high susceptibility for the greater area covering these landslides. For some other areas, like here, these are mapped landslides, and we have identified high susceptibility, and with orange, moderate susceptibility. With green, of course, there are some cases where there is we have low susceptibility like here, and there are some mapped landslides. This could be the case, as I said before, with dormant, inactive landslides due to this, and the difference between the periods of the analysis. So, summary, some future steps. The differential interferometric spheric aperture radar-based susceptibility mapping should be used combined with conventional landslide inventories to ensure that inactivated landslides are also included, because the dormant landslides can be activated at any point. Also, rainfall intensity could be included as a parameter if rain gauges data are available. And the combination of parameters for deriving susceptibility models can also be examined, like combination of, let's say, maybe the geology with the rainfall, combination of the parameters instead of looking them in isolation, separately. And conclusions is that the DINSAR method we just presented can be used to easily update inventories to include new landslides and newly activated landslides. It offers retrospective analysis, and it can show the extent of landslides as well as the magnitude of movement. So for these defined landslides, we have also the magnitude of the movement, but also have to consider limitations of this method, like we explained the east-west decomposition of the east-west direction of horizontal movement. So this is a limitation because it can only be displayed in this direction, in horizontal. Also, the vegetation presence and how to handle this, the atmospheric effects, which can cause the coherence of our data. And where measurements are required at specific locations, we can have installation of corner reflectors to ensure that specific measurements are taken at specific locations are considered in our results. So thank you very much for your presence on this presentation. I'll be happy to answer any questions you may have.
Thank you, Dr. Perdikou, for this very insightful presentation and talk. We had quite some questions in the chat, but I will not go through them now because most of them were answered. So we will take some time for additional questions. There is one question. Thanks for the great presentation. Is there any example that a landslide is predicted by this technique before case happened?
Any examples of predicting before they happen?
I think yes.
Yes. This can be, yes, this, because with these methods, we can detect slow moving landslides. This is the idea. You can detect movements even at small rates. We set up a threshold of 30 millimeters per year for this analysis. So you can, in fact, identify slow-moving landslides before they cause damage or problem to the properties. Yes.
Thank you. And we have another question. First, thank you very much for the interesting presentation. Could we combine optical with SAR data in order to monitor landslides, and in which way?
Yes, of course, optical data can also be combined. You can, I mean, in different ways. For the, let's say, for the vegetation coverage, we used optical data for the enhanced vegetation index. You can use optical data to see differences and changes on landslides. Say in the same way that you can observe changes and traces of signs of landslide, of movement of the soil, or identification of landslides using either aerial photography or high resolution satellite, optical satellite images. It's one of the methods that actually is used for being able to obtain signs of landslide, but of course you need a trained eye, let's say, for that. That's why I said earlier that it is used for landslide inventories, conventional methods, but it needs a great expertise to be able to identify this. But there are a lot of examples in literature, and it's something we are also using optical data for getting signs of landslide from images. Of course, either changes of vegetation or from the soil. Yes. So the answer is yes.
Thank you. We have another question. What is the highest velocity that can be detected by this technology?
This has to do with the data set and the landscape. It's, when I said earlier, millimetric accuracy, you can detect even 2 millimeters, let's say, for example, per year, mean annual velocity, because for each of the targets we detect, we have its mean annual velocity. The important thing here is to be able to evaluate whether this movement is attributed to a landslide. That's why we set up a threshold of 30 millimeter to exclude any soil creeping or any classified movement, because you might have any, let's say, some excavation happen on one side, which the analysis could misclassify it as a movement, which is not actually a landslide. It's a movement of some material, let's say. So it is important to be able to evaluate your movement and be able to see whether this is due to a landslide or due to any other activity. And that actually reminds me of the previous, associates this answer to the previous question of where can we use optical data. Optical data can be used in actually to exclude activities that are not landslide activities. For example, there was 1 or 2 examples in our studies. You might have a mining near in your study area or a construction site. So if an area shows high displacements, you might think it's a landslide, but actually by looking at time series of your optical data, you can see that this is actually a mining activity, it's not a landslide, or this is a construction site, which is misclassified. So you need to look at the time series and the progression of your data to be able to determine whether this is a landslide or not. But regarding the question, you can identify even very slow moving landslides, even of 5 millimeters per year.
Great, thank you. We have another question. Actually, quite a lot of questions for you. Is there any manual for running methods like PS and SBAS?
Yes, there are actually quite a lot of, there's quite a lot of literature, and this also, I'm not sure about manuals. Usually the manuals are associated with the software that people are using, but there is a lot of information available on literature of related to the PS and SBAS. I'm not sure about manuals because it's depends on what software each one is using for this.
Okay. There is a question regarding the presentation. Just to inform you that we will be uploading the recording via YouTube, and we will be sending this to you by later today or tomorrow.
I also wanted to mention here, sorry, Eleni, it's that there is a paper associated with this presentation which has been accepted and to be published in Natural Hazards. So it's going to be published soon, and it provides a lot more information. It's about this method and what we have done, if people want to look at it in more detail.
We have another question. A next important step would be the establishment of an early warning system so that we can use advantages of SAR to prevent loss of lives. Actually, it's not a question, so maybe if you want to comment something on this.
Well, I absolutely agree. This is all this data and all this analysis can be useful for early warning systems, as I said, combined with the conventional inventories and other data. Of course, it can be very, very useful. And the fact that this analysis can be updated regularly, let's say after winter or rainfall seasons, wet seasons, it can provide a lot of information about the displacements in an area and about the susceptibility of an area to landslide, which is very important and great input for early warning system. And I agree that the next steps should be the development of early warning systems.
And one last question, and I think we can close today's talk after this. What about the combination of all these data sets with artificial intelligence, fusion data, SAR, optical, and vector data?
Again, absolutely agree. It's something I didn't mention, but it's something we include in our analysis. The artificial intelligence in our models, and of course, yes, I agree. It's something that is useful and something we are already including in our analysis. Yes, definitely. I would also like to say that I have my email address here. So if people think of any other questions, they can send me an email and we'll be happy to answer any questions they have.
Thank you again, Skevi, for today's talk and all the participants for joining us. Also the rest of the Geofem team for assisting today. Before closing, I would like to take the chance to announce our upcoming invited talk by Dr. Kleanthis Nikolaidis, the director of the Department of Meteorology of Cyprus, with topic The Science of Meteorology and Remote Sensing Applications. This will take place on Thursday, the 12th of December 2020, and at 12 o'clock Eastern European Time. We will be informing you about this via email as well. And yeah, thanks again. Thanks for joining us today, and hope to see you all in our next invited talk. Have a nice day.
Thank you very much, everyone.
Thank you.